Okay, hello everyone. Welcome back to a new session, Computer Science 2. Today we are at 4A. We just finished with test 1. I sent an email regarding test 1 about 2 mistakes that we found in the test. So today we are here. Our main focus on dynamic memory allocation. I already assigned you homework 4, so let me know if you have any questions or you need help. And regarding the test, I just sent this email. You need to pay attention in case you got this true and false question. The answer should be true. So if you answered as true, but you did not get the grade, you need to reach out so you can get your grade. In multiple choices, there was this question, and the answer should be only one. So in case you answered as only one, but you did not get the grade, reach out so you can get the grade. And homework 4 has been posted. So I have the book next to me. I'm on page 530, which is topic 9.8, dynamic memory allocation. Dynamic memory allocation as an idea is that your program will allocate and release memory on runtime before after compilation time. So if you remember from previous sessions, we declare variables with data types basically to tell the program how many memory do we need in bytes. For example, in case I declare an integer, I'm telling my memory for this holder or carrier, I need 4 bytes. And this should happen on compilation time, means before I start building my program. So that when my program runs, all the memory for that program is already allocated. However, you can have some flexibility, of course, through some STL containers, standard template library like vectors, maps, and we're gonna go over them in chapter 17. Or you can do dynamic memory allocation using pointers. So this is the concept. The concept is variables may be created and destroyed while the program is running. You allocate new memory and you free up that memory. Then you allocate a new memory, you free up that memory. For example, if I had an array integers, notice the compiler before I start building my program asks me, hey, well, you need a size. I need to know. The compiler is saying I need to know how many bytes for this array I need to allocate. So in case I put 5, I solved it. In case I put L user input, means I need to ask the user input for a size. Also, the compiler is not gonna like it. For example, enter the size CNL user input. It doesn't like it. It says, hey, this needs to be constant and needs to be initialized on compilation time and not on running time. The fact that I'm asking the user, that means the program is running. So I cannot allocate memory using this way. What I need is 2 keywords, basically. The first keyword is a new. The second keyword is delete. For the new, I can use it for both variables and arrays. However, the delete for variables and delete with the square bracket for arrays. These are the main 2 keywords. These are the only keywords for dynamic memory allocation. Anytime you're dealing with dynamic memory allocation, you're gonna be counting on new, the calls for new, and the calls for delete. You're gonna call new to allocate memory, and then you're gonna call delete to release memory. And the rule of thumb is we should not keep any memory allocated. In case we use only new without delete, that means my program is allocating memory forever. It keeps allocating memory without freeing it up. So at some point, my hard disk is gonna get full, no more capacity to allocate, and then my computer will basically gets to a be blocked basically. If I'm allocating memory and there is no free memory, then my program is not gonna function as expected. So the rule of thumb is anytime you use a new, you need to use delete. The same number of calls for the new should be equal to the same number of calls for the delete. If I call a new 10 times, then my program should be calling delete also 10 times. Means every block of memory that my program allocated, my program should release it as well. I allocate some memory. Once I'm done with that memory, I should release it. I should not allocate a new memory before releasing the previous memory. So again, the rule of thumb is number of new calls should be equal to number of delete calls. And I'm saying calls, not statements, because I can have the keyword new within a loop. For example, if I have a loop and I have new call in it, let's say this goes from 1 to 10. Let's say it goes 10 times. Here I have only one statement for a new, but the total number of calls is 10. So I can't just say, oh, okay, I have only one new in my code. It's on only one line. I have only one new keyword, so I should only use one delete call. So no, the number of calls should be equal. If you're calling new 10 times, then you should call delete 10 times as well. Every variable you call the new on it, you should call delete on it as well. So let's demonstrate a little bit. These are the definitions or the notes for you. So traditionally, I can't do it. I should have it constant and initialized on compilation time. However, with the new keyword, I can now uh, do exactly that. So what I can do is I can say, okay, I have a pointer to an integer and it's gonna point to some memory. That memory can be with a specific size or one item, exactly one item. So I take the input from the user and then I say I need pointer to an integer that points to integers, and it is new integer L user input. New int. So now what I told my compiler on runtime, after asking the user what I told my program, I told my program, go allocate memory, new memory for me. For the data type integer means 4 bytes every item, and I need this size of integers. So the total size would be the number of items multiplied by the size of each data type. So if the user enters 5 and I know that every integer is 4 bytes, then my integers will have 20 bytes in size. Now this will be accepted by my compiler. I can then tell the user, okay, enter next value. Cn into L integers at, for example, I. And I can do that. I can iterate based on the user input. So if the user entered 5, I will be iterating 5 times. Now that I iterated and populated this array, I'm going to iterate it again and this time see out it. just so we see what's in my array. What's the warning? Oh, reading invalid data from integers. The readable size is 4 bytes, but 8 bytes may be read. That's fine. Run. So enter the size. I need 5. Then it's gonna iterate 5 times. 10, 20, 30, 40, 50. Now that it iterated 5 times, I iterated again and displayed them. So during the runtime, while the program was running, I allocated memory and I populated them and then I accessed them. But I forgot one thing. Right now, this program allocated memory for for 5 integers, but it didn't release that memory. If I keep running this program over and over and over again, I'm gonna basically take over all the free memory in the system because I keep allocating without releasing. So I go back. Once my system is done, or my function is done, or my task is done, or the process is done, I should release the memory. So I can say delete as an array, because this time I'm deleting an array, not one single value. Delete integers. So this will release the memory. Then after that, the rule of thumb is to set it to be null. Always after deleting, set it to be null. This way, sometimes, and some compilers, some programs, if you run delete and then you run a new again, it just doesn't like it. Some programs and compilers would like the new call to be called on a null pointer or a new pointer. If there was a pointer that you used before and you're planning to call the new keyword again, you better set it to null before calling the new again. So this is just a good habit to have. Integer is allocated with scalar new with deleted array, but deleted with array. Well, yeah, that's exactly what I need. Why it's yeah, this is exactly what I need. Will it like it if I do this? Yeah, strange. Okay, so now if I run, nothing is gonna happen. Same. I need 4, 10, 20, 30, 40. It's gonna display. Oh. Retry. It's still running. Go. I need 5. Go. I need you to go all the way here. 10. Continue. 20, 30, 40, 50. Okay. So integer now has values. This is the address and this is the first item. Delete it. Let me think. Oh, you know what? This might be the problem. I think it understood it as a constructor instead of size. We need the square bracket, my bad. I need pointer to integers and the size is user input. So now it's gonna understand that it's an array. It's not a single value that has been constructed using this value. So now that I told it the size is 5, reading eval data from integers. Well, I'm reading into integers. The size is 4 byte, but 8 byte may be read. Okay. Is this still the same? Well, let's run it and see. The size is 5, 10, 20, 30, 40, 50. So now integers has 10 in it at that memory. Delete the entire array. Now, see, it has some junk. So I better set it to null. Now that it's set to null, I don't understand this question mark. Okay, so this was the idea of dynamic memory allocation. So I'm gonna do more practice just so you can understand fully the concept. I'm going through the book. So concept, the topic 9.8, it says dynamic memory allocation, page 530. Then it speaks about the concept. It gives you some examples on how to allocate with the new keyword. Then a graph, how graph 911, figure 911, it shows you how there is a pool of unused memory, and then your program goes and grabs a chunk of the memory, starts at address X up to Y, and then your program starts populating and accessing that chunk of memory. Once it's done, you call the delete, and then that chunk of memory that your program allocated will be released back to the pool of unused memory. That pool is managed by the operating system. Your program communicates, and every program communicates with the operating system, and then the operating system communicates between your program and the hardware. The operating system is basically the manager, the controller. It is the operator, the operating controller. So let's do the example in figure 9.14, which is about totals and average of sales amounts for a number of days. So there's a company, it has sales, and these sales are throughout the days. So notice we don't have any errors anymore. It was because of this square bracket. So I'm gonna take this off, and then I'm gonna do a simple example about a company with sales. So I'm gonna need a pointer to sales, and that's a single value. I need a pointer to total, and that's a single value as well. I need total. I need a pointer to an average, and that's a single value as well. And then I need the how many days, and maybe how many sales on total if we have more than one sale per day. So I'm gonna go ahead. I needed a double to be. First one is the sales, null ptr. I need the same for a total, and then an average. So total, average, and then I need int for days. I need int for count. Then I'm gonna start asking the user basically, how many days of sales without the end line, cn into l num of days. So l sales, l total, l average, l num of days, and then l count of sales. Now that I grabbed those, this will act as the array, this will act as a single value, and this will act as a single value. Single value, single value. In this case, if we are taking into consideration more than one sale per day, um, this is array to dynamically allocate memory. So how many days? I need this number of days. So let's go and allocate memory for that exact number of days. So I'm gonna say L sales equals new double, right? I have array of doubles. So I need a new double for this size. Now that my program on the runtime allocated this memory, I'm gonna start asking the user to enter uh, the sales in order. So I'm gonna say enter your sales. Now that I told the user, I'm gonna iterate from 0 to num of sales. How many days? Yeah, okay. So one sale every day. Then I'm gonna say cout day I plus 1, so day 1 on the first. So day 1, the user is gonna enter it. I'm gonna cin into whatever my array at this location. Then I'm gonna cout an end line. This should go over one by one, right? And boom, 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 yep. Now that I took from the user all the info, I can calculate the total in one loop. I can calculate the total in a different loop. Just for the sake of demonstrating and keeping things clear and separate, I'm gonna do it in a different loop. But I could have do it on the fly, right? Every time the user gives me a sale amount, I just add it to the total. I can recompute the average on the fly. But for now, I'm gonna keep it separate, just because we are under educational settings and explaining things. So now that I took those, I'm gonna say, okay, for I equals 0, I less than L number of days, which is basically the same loop. I'm gonna say L total plus equals, and this L total, I need it to be new. Okay, so L total is we don't need it as a pointer, as a matter of fact, and average, I don't need it. I only need the array to allocate. So I'm gonna say this starts from 0, and average as well starts from 0. And then here I can say L total plus equal, because it started from 0, plus equals sales on whatever this index or subscript it is on. Now that I have the total, I can calculate the average by saying L average, which is a double, equals L total, which is also a double, so I'm good on the casting, over L num of days. Now that I have the average, I'm gonna just see out the result. So I'm gonna say total is L total, and L, I'm gonna see out average is L average And maybe because we're gonna have some doubles, so let's fix the precision. So I'm gonna say fixed and show me it as is, and 5 maybe set precision. So since it's not suggesting it for me, that means I need a library. Include IO manipulation. Yep. Now it should suggest it for me. So set precision. Here it is. Set precision. I need it to 3. Now that I did this and I finished my task, how many times did I call the new operator? I called my new operator only once. Here it is. I only called it once, and I called it on an array. So the same call for an array and variables, but the delete, it has a different syntax for an array. The fact that it's an array, I'm going to say delete with bracket L sales. Now that I deleted, I set it back to null PTR. Now I can run. So sales, it's null, total is 0, average is 0. I ended up not using this. So how many days of sales? I'm going to say 3, just so we are simple. Number of days is 3. So go ahead and allocate memory. Enter your sales up to 3. So day 1, I'm going to say 10. Day 2, I'm going to say 20. Day 3, I'm going to say, so we have, let's put it total to 60. So go. So now compute total. Now it's 60. Then average is 20 because 60 over 3. Now set it to fixed. Average is this. Total is this. Delete sales. So now it's deleted. Now it's null. And program finishes. Let's have some decimal points this time. Let me close all these. Don't need this too. Let's do again, but this time with some decimals. So 5, 13, 25, 40, 11, and 42. So now I have decimals, only 3 precision. Here's the total. Here is the average. 131 over 5 is 26.2. My program ended and I released the memory. Here you see this diagnostic tools. At some point, if I am allocating big memory, it's gonna show me here that you or your program basically is using this much of the CPU, this much of the memory, this much of etc. So at some point, if I keep calling new without calling delete, you're gonna see that the memory is increasing. Right now it's 823, but it's gonna be more than that, and it's gonna be increasing. And when I shut down my program, that memory did not get freed up. So operating system will not know about it, will think that the program still allocates it. It's similar to when you open the file without closing it. So when a task or a process opens the file without closing it, it denies all other usage or uses for the file from different processes. If a different process comes to open the file, it's going to be denied, and it's going to say the file is being used by some program or some process. So similar fashion, if my memory allocates memory that memory is being used by my program. If some other program asks for memory, the operating system is not gonna give it memory from my chunk. It's gonna go to a pool of unallocated memory and give it some memory. If my program takes over all the pool of free memory, then no other process will work, and even my program in future will not work because no more free memory in the pool. So as much as dynamic memory allocation is important, deleting and releasing the memory is also important. This is pretty much it for dynamic memory allocation. Let me see the book. The book speaks about examples for dynamic memory allocation, just like how we mentioned. Then we go to topic 9.9, returning pointers from functions. I'm pretty sure you know how to return a pointer from a function, but there is a key point that I need to point out, which is remember the scoping rules for variables. If I create a local variable, once within the scope, this variable is only available within this scope and any inner scopes, but not outside the scope. For example, if I have another scope or a for loop with a scope, integer is available inside the inner scopes. I can use integer here. I can use integer in the for loop, but I cannot use integer outside the scope. And not just that, once this scope finishes, once the control is done executing, this variable will be destroyed, will get destructed. So if I have a method that says, for example, give me return anything. So int return anything. Return, I'm gonna create L integer, right? I'm gonna give it 5. And then I'm gonna return it. This will return a copy of an integer. By the time the control reaches this end here, L integer will be destroyed. So you basically returned, or I basically returned, a variable that is about to be destroyed. So be careful with this case or with this example. We do not want to return any variable that is about to be destroyed, especially with pointers. The only you should return a pointer from a function only if it is within two cases. The first case is you are returning a pointer that was passed to the function. If a pointer was passed to the function and then you did, or your function did some task, you're allowed to return that pointer. And the other case is a dynamically allocated pointer. So returning a dynamically allocated chunk of memory. Only in these two cases you are allowed, or it's fine to return a pointer. If you are returning a pointer that was passed to the function, or you are returning a dynamically allocated memory. For example, here is this, for example, and I have int L integer equal 5, L integer ptr equals the address of L integer. right? I'm constructing the bad example. So this is a bad example. Semicolon, and then I'm returning this. Let's return a pointer. I'm returning this pointer. Now I'm gonna see out, return anything. I wrap it, and then I dereference it. So this will return a pointer, and then the outer scope will dereference that pointer to display something for me. Run. It might probably display 5, but that memory is not mine anymore. So that memory has been released. This got destroyed. The value is still in the memory. Let me explain exactly what's happening. So I created an integer and I put 5 in it, and then I referenced that integer. So now this pointer is pointing to a memory that has 5 in it. When this scope finishes, this integer will be destroyed, this pointer will be destroyed. The value 5 will stay in the memory. There is no variable referencing it, there is no pointer referencing it, but the 5 is in the memory. The fact that these two got destroyed means the memory they were using became free, back to the pool. Yes, there is 5 in that memory slot, but that memory slot is free for some other process. Imagine between this section and this section, imagine there's a lot of codes. Let's say this was done and it's pending, right? This has been done and the value is ready, but your program is doing something else and it takes 10 minutes. And your program is allocating memory, other processes are running on that PC, and the value that the function returned is ready. However, during those 10 minutes, your operating system gave that slot, wherever 5 was, gave that slot to some other process. And then your cout came to use that slot. It's gonna say access denied and the program will crash. Another way to see that happening is by saying, for example, go here, right? Go here, and then I'm gonna say for int I equals 0, and I'm gonna go maybe million times. I less than 1 million, I plus plus. I'm gonna say at this point, cout 0. I need you to see out the value in this address. And after you do that, go to the next slot. So I'm gonna go over 1 million slots. Some slots are free and some slots are used by other memory. The program is gonna keep going over the free slots, and as soon as it hits a slot that is used by another process, it's gonna crash. See? Read access violation. Now I don't know at which slot, maybe 100. So notice, look, there are values from previous stuff. So this is my 5. Then I jump to the next one, junk. Next slot, junk, 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 junk. Oh, not a junk. Oh, not a junk. So there is a value in that slot that has been used in the past, and the process released it, but it didn't delete the value. It doesn't delete the value, but the slot becomes free. So, oh, here's another one. Here's another one. So I can find maybe clearer or nicer values, not just a junk. 0, for example, null. But at some point, I'm gonna reach a slot that is being used by another process, and it's not gonna allow me, and it's gonna crash my system. There is no way I can continue, especially in C++. In C++, if you have one error in your program, the entire program crashes. Unlike unlike JavaScript, for example. In scripting languages, if a function fails, only that function fails, not the entire program. The entire program is not going to crash. Only that function will fail and will return some junk. In C++, if one line fails anywhere in the program, the entire program fails. See, I cannot continue anymore. There's no way I can continue. So with this example, notice how I was able to just go over memory and access them until I reached an allocated memory. Similar idea or similar concept or similar consequences can happen when I return a value or an integer or a pointer that is about to be destroyed. At this point, when cout happened, actually let's split them. Auto L result equals this, right? I split them. Imagine between this line and this line, there is 1,000 lines of codes equals to 10 processes, 10 tasks or processes. Or between this line and this line, I have 1,000 lines of codes. I'm doing 10 tasks between here and there. When this got executed, I have the value here, but the memory has been released because this has been destroyed because the scope ended. When the scope ended, these two got destroyed, but result is still pointing to that memory address. Result is still pointing to that memory address, and here I'm trying to access it. However, some of these tasks went ahead and allocated new memory, and the operating system gave it the address of result. Now that I'm trying to access that memory slot, it's not going to allow me, and my system is going to crash. So back to this point, you never do this above. You only return pointers in these two cases. You only return pointers in case the pointer has been passed already to the function, or it was dynamically allocated chunk of memory. Why? Because if it was dynamically allocated and you did not call delete on it, that means it's still allocated for your system and it will never be deleted. I will never have this case if it was dynamically allocated memory, because with dynamically allocated memory, I am the programmer who controls when will this be freed. So the fact that it was declared within you, even when the scope ends, it's not gonna destroy it. It's not gonna free up that memory. So anytime in my program, I can still access it. Right before I exit, I delete L result, L result equals to null pointer just for the habit, and then I'm good to go. So this is safe. This is one of the cases. This is safe. I'm returning a new allocated memory that has copy of integer in it, 5. The scope ended, the memory is still allocated because I used the new and without using delete. Now I can do my 1,000 lines of code, I can do my 10 tasks, and it's guaranteed that the result is still allocated for my program. In case I access it, I will be allowed, and it's not gonna be denied, and my program is not gonna crash. Notice the delete is without bracket. Without a bracket because I'm not deleting an array, I'm deleting a single value. This is a single value constructed based on integer. However, if I tell it I need integer, integer ptr array equal new int with a square bracket, now it's an array. So this one is a single value with a constructor. However, this one is an array of integers, no size yet. I can give it 5, I can give it 1, I can give it whatever I need. So this is what the topic was trying to say. If you didn't fully understand me, send me more questions, send me questions, and maybe read topic 9.9 if in case you still need more info. With that being said, the last topic is 9.10, speaks about using smart pointers instead of pointers. Starting C++ 2011, which is called C++ 11, they introduced something called smart pointers. And smart pointers do the same exact thing like pointers, dynamically allocated pointers, but the only difference is with the smart pointers, they clean after themselves. So the programmer doesn't need to actually delete the array or the pointer. Smart pointers will delete themselves after every use. Once the scope ends or the program shuts down, they clean themselves. And we have 3 types of smart pointers. We have unique pointer, shared pointer, and weak pointer. Unique pointer is basically a sole owner of a chunk of memory. Unique pointer, nobody else points at that memory but that pointer. You cannot find 2 unique pointers that can point to the same chunk of memory. And when a unique pointer goes out of scope, it automatically deallocates the memory. It automatically frees up the memory. Then you have shared pointer, which is like the opposite kind of unique pointer. Shared pointer means this pointer along with other pointers are pointing to the same memory. It can share ownership basically of that chunk of memory. And you can have multiple shared pointer, obviously multiple shared pointers pointing to the same memory. Similar to unique pointers, shared pointers will clean after themselves. And if you have multiple shared, it only cleans itself after the last shared pointer is about to be destroyed. Not when the first, let's say I have 3 pointers pointing to the same memory address. If the scope ends on the first one, it's fine. It's not gonna deallocate it because we still have shared pointers. If the second one gets destroyed, the program doesn't deallocate memory because we still have one pointing at it. So there is always a count in the background that keeps track of how many pointers are shared on this memory address. Once the last pointer is about to be destroyed and no more shared pointers are pointing at that memory allocation, only then it releases the memory. So we have unique pointers, shared pointers, and then we have weak pointers. Weak pointers are similar to shared pointers, but they are not taken into count. Means if I have one shared pointer and one weak pointer pointing at the same memory address, once the shared pointer is about to be destroyed, the memory gets released. Even if I still have a weak pointer pointing to it. And it's called weak because of that. It's not taken into count. Once all the shared pointers are destroyed, then the memory will be freed, even if I have 1 million weak pointers pointing at that memory address. So that's basically it for dynamically allocated memory. Let me see what the book still has to say. They have a case study, which is sorting an array. That's for you if you need to practice. And that's basically it. Nothing in the book. Yeah, okay, so for next time, where are we at? We are at next time, I think structured data. So next time is, yeah, structured data. So this is next session, which is like Wednesday or Thursday. And homework is due midnight Sunday. And the project 2 is also midnight Sunday. Then on Monday, I'm gonna assign you homework 5 and the project 3. So let me know if you need any help or you have any questions about pointers, specifically dynamically memory allocation.